All right, a 5 kilogram ball is dropped from a height of 3 meters onto a vertical spring. Okay, so here's a ball that's 3 meters high. Okay, which has a spring constant of 800 newtons per meter. Okay, so here's an H, here's a mass, here's a K, all right? How much will the spring compress, so that's an X, as the ball comes to a stop at ground level? Assume 10 joules of energy are dissipated by air resistance during the fall. So that's the thermal. That's, oops, let me write over here. That's E thermal, okay? All right, what is wrong with this thing? Okay, all right. Okay, so my initial picture would be, I guess, let's say top, and then the bottom, let's say it's at the ground, okay? So it says that the spring is gonna compress at the ground level. So somehow, right, like this spring has to be able to compress like all the way so this is on the ground, okay? So the spring, I don't know, maybe there's like a little pocket here and then the spring like squishes into it or something, who knows, all right? So that'll be the final, okay. All right, so let's see what we've got. Okay, so in the initial position, is there any EG? Yes, because it's above the ground. Is there any EK? No, because it says dropped, so that's a no. And then is the spring stretched or compressed yet? No. And E thermal, there's never any E thermal, okay, in the first position, all right? So we're gonna have only EG, so that's easy. So MGH, oops, why did I write that again? Okay, the mass of the ball is 5 kilograms, the G is 10 meters per second, and the height is 3 meters. Okay, so that's gonna be 150 joules, all right? And since there's nothing else, I know the total has to be 150. Okay, and then conservation of energy, this total has to be 150, that's a given, all right? So let's look at the second position. Is it above the ground? No, so that's a 0. Is it moving? No, because it says it comes to a stop. Anything stretched or compressed? Yep. Okay, and is there thermal? Yes, it's 10 joules. All right? Okay, so now what you have to do is we're going to have 1/2 kx squared. All right, and I'm looking for the x value. All right, so I'm going to have to isolate that. So I'm going to get 2EE over k is x squared. And then I have to take the square root, 2EE over k. Oh, it's very tiny, okay? All right, so then my x is gonna be 2 times the EE, all right, over the k, which is 800 newtons per meter. All right, now the tricky thing is what goes here, all right? So if I have 150 joules total, and then 10 of it got wasted, right? That means that I'm only gonna have 140 joules. Oh, that was not right at all. Okay, I'm only gonna have 140 joules left, all right? So that means in my graph, so let's think about it. So let's go, I don't know, 50, let's just label these by 50s, I guess. It's a little small, but whatever, okay? My initial is gonna be EG of 150, and then nothing here. 50, 100, 150, okay? And now my thermal is gonna just be like 10, and my EE is gonna be 140. Okay, right? That's how I know what to put here, okay? So 2 times 140 divided by 800, okay, is 0.35, and then take the square root of that. That's 0.59 meters. Okay, and I'll go ahead and write this up here.